All right, so we have an interesting problem that I want to spend not the whole rest of the period on, but we're going to spend some time with this. We're kind of getting to the point where you guys have seen everything you need to see. It's time to apply it and understand, okay, what's the difference between these two problems? Is there anything different about them? Well, there is. That's actually kind of the first thing. It's just like realizing, oh, there's something different about these. By the way, I'm not going to just like come out and say it. Look at the first one. It says to evaluate the integral of sine x minus cosine of x from pi to 2 pi. Looks kind of like a good old problem. Actually, if I had not put the second problem down here, I wonder what you guys would have done with the first one. Usually my hint there is do that. If I hadn't put two of these problems and just gave you the one at the top, what would you have done? I'm going to kind of challenge you and say do it. But there's something different about the second one. It says to find the absolute total area. I'm putting a little emphasis. I put some extra words in there. Remember the book never uses the word absolute, but I kind of wish they did. So what's different about that one? I just want to encourage you. This is one of those times, it's not an exit ticket, but it's just one of those times where just mess around with this a little bit. What would you do with the first one? And then, well, we'll get into and see what's different about the second one. But see if you can just get an answer for the first one. There isn't anything, I'm being honest with you here, there isn't anything about the first one that requires any special thinking. Okay, now, anytime you're doing something with trig functions, sine and cosine, it's always good to be careful. It seems like a lot of times numbers come out to be 1 or -1. You do get some 1s and -1s for this one. They don't subtract to be 0. I just saw a couple of you with a 0. Just want to be careful about that. And maybe it starts with the antiderivative. The antiderivative of sine is opposite cosine. You kind of have to think backwards from the last chapter. Now, the antiderivative of cosine is sine, but the minus sign, notice I didn't do anything with it. I'm just thinking of cosine. So the minus sign doesn't cancel out, doesn't disappear. So it's an interesting antiderivative. It's not the opposite. It's the antiderivative. I change these functions. Okay, now when you plug in 2 pi, some of you might find yourself in a college class where the professor's like, you can't use a calculator. I know Penn State, I've heard that there's some that are like that. Does that kind of make you panic a little bit? 2 pi is a place on the unit circle. It's over here. Okay, it's basically the same as 360 degrees. Now that place always has an ordered pair known as 1, 0. And of course, the 1 is the cosine and the 0 is the sine, because cosine is x and sine is y. So if you plug in 2 pi here for cosine, you get 1, but -1. And if you plug in 2 pi for sine, you get 0. Either way you shake it. If you put that in your calculator, you get -1. Pi is a place. It's a rotation. It's halfway around a circle. Okay, if I plug in pi, if I plug in for cosine, I'm looking at this -1. But this negative sign here is going to undo that. I still get 0 for sine. Okay, so -1 minus 1. -1 minus 1. Let me show you something on the calculator. And this is not number 2 yet, or the second question. It's still thinking about this problem. I have an equation in here from another period, but just so you can see, I typed in sine minus cosine. Like I typed in the original function. Careful, we're not graphing the antiderivative. Not yet. Okay, we'll be doing that in the next chapter. Bet you can't wait. But we're just graphing the function. And, probably hit zoom trig on a TI. I want to change the window because something I want to show you here goes right up to 2 pi. So depending on how familiar you are with the calculator, the window stops at 2 pi. So I'm going to go a little bit past. I'm going to go to 3 pi. I just want to see a little bit further. Okay, so same graph, but a little more space. Now, the answer is negative. Okay, these are things that, I don't know if I expect you to write an essay about them, but to understand that since the answer is negative, there must be more negative area. There must be area below the x-axis. These are all things that are fundamental to this chapter. Even though we're doing a lot of new things, remember the basics. So, where is this area? And this is a little something I want to show you. It's not a secret. Maybe some of you discovered it. It also, you don't need to use this, but on a TI, if I go to the calc menu, which is second trace, now this is the graphing calculate menu. I actually get, on sort of the basic TI, I get an integral sign. Okay, in other words, we're going to do the area. Okay, the way this works is that it requires me to, on the graph, to tell me my limits of integration. Now it's pi to 2 pi, so I'm going to go to pi. I actually typed in pi, then I'm going to type in 2 pi, and then it does its magic. Now, again, this is kind of nice. It visually shows us what we just found. It visually shows us that there's a lot of negative area. Okay, but there's a little bit of positive area. But the truth is, when you put them together, we end up with a net area of -2. We end up with a net of -2. Okay, and just so you guys are clear, that's what this was doing the whole time. I didn't need to look at a graph to get that answer, but it is what the graph shows, a net area of -2. Now, the reason I'm using that word net is because it takes the positive with the negative, which brings us to the second one. I'm not sure how far you got with it, but did you realize that the second one is actually asking us for the absolute of that area? If I could just find what this little pi piece is, if I could just find what this big chunk is. Now be careful, it's not like one of those is -2 and the other one, no, none of those are -2. If you put them together, you get -2, but what I want to do is I want to find them separately. So when you see something like that second question up there, you have to automatically think subdivide. You have to think separately. Now, you've heard me say these things before. We actually did them in a section or so ago. But that's the way this chapter works. We kind of bring it back up. So we're going to subdivide. Do you remember how we subdivide? I forget if I did this live or remote, but x-intercepts. And that's exactly where those two areas seem to stop and start, at the x-intercept. Okay, now you can kind of do whatever you need to do. This would be a calculator question. Like I would give you the calculator tool. So, the x-intercept happens to be a command on the calculator. I'm in the calc menu again. It's the 0 command. And so I think we can see that there's an x-intercept that's somewhere over here. It turns out that I can trace close to it, but that's not exact enough. But I can get close. It's like right around 395. Have you ever used the 0 command? You have to put the spider to the left and hit enter. And then you put the spider to the right and hit enter. And then you put it back in the middle. It's called left bound, right bound. So the calculator actually zeroes in. Now it's close to 390, but it's 393. It's 393. I know I've said this before, but we're all here to keep learning. So don't forget, it's good learning to, when we're doing a problem visually, to make a sketch. Have you put a sketch in your notes? Okay, do you realize that we're finding these two separate areas? But of course, I just found this x-intercept to be 393. And that's a pretty important number. I'm just going to pause again. You can do as you wish. You can just catch your breath, or maybe you want to consider starting something on this. We actually have done a problem similar to this, so do you know what you would do? I've given you some pretty good things to start with. If you want to take a peek, what I showed here is it's really an always. You're always going to be splitting it up into separate integrals. I don't know if this seems like a lot of work. There are some things that you could use from the previous problem to help with this. I'm just providing a little bit more of a template here, because basically you just need to determine these three values. We already determined two of them, so there's only this new one that we have to find. Okay, now, this is a good problem to just experience all the subtraction. I mean, the calculus is kind of over. Now all you got to do is just carefully subtract these numbers. Are we being careful about that? Okay, when you subtract for the pink region, it's 0.41, which again, we should look at that and say, okay, good, it's positive. And it's not much, right? Like 0.41 is not a real big space. That's all good. That's kind of what we hoped. Okay, when you do the yellow space, again, I have to admit, when I first wrote that down, I'm being honest, when I wrote that down 5 seconds ago, I was like, oh, wait a minute, is it backwards? It's not backwards. It's f of 2 pi minus f of 393. It's going to be negative. Like, that's good. It's going to be negative. Okay, because again, this is a negative space down here. But of course, the reason we subdivided it so we could, in a sense, negate the negative. So we could do the absolute value of these. This one's already absolute. This one needs to be absolute. I want you to notice the difference between these two answers. Also kind of want you to notice how the two answers connect. because you could get our first answer by doing all this. It would be a lot of extra work, but you could have taken negative 241 and 41 and still came up with negative 2. But the reason you did it this way was so you could subdivide it, and so you could make it an absolute value of those subdivisions and end up with the absolute total area. Okay, now a lot of times kids will look at what we did here and say, oh, it doesn't sound too hard, I can do that. Yeah, I think you can. I think usually it's just realizing, and I'm going to mix a problem like this into other problems. It's just going to look innocent, but as soon as you see this, you have to do this. You have to subdivide with those x-intercepts, okay? And that means a graph. It means looking at a graph so that you can get that set up. Yes?
So we can still get the negative 2 from the absolute value.
You could. Be careful about that. I'm only saying because kids will make this problem too hard. If I give you this problem, just get her done. But if I give you both problems and you're like, wait a minute, I could just kind of do all the work over here, okay. So, but my caution is don't make this problem too hard. It does not need to be subdivided. And I know you're not saying this, but sometimes I'll see kids like all of a sudden every problem like this becomes this. Don't do that either. Before lunch, we just did 5 problems that I didn't even talk about the graph. You just did them, okay? You only have to think about subdividing when you have total absolute area. Tomorrow we'll do a little application, and also we'll have a pretty good group of exit problems. It's actually a larger exit this time as we get closer to a test. The test is not this week, but